All right, today we're going to be analyzing graphs of polynomial functions, and these are the content standards and the mathematical practices we'll be using in the assignment. You have previously used maxima and minima and graphs of polynomials. And now we're going to graph polynomial functions and locate their zeros and find the relative maxima and minima of polynomials functions. New vocab today: location principle, relative maximum, relative minimum, extrema, and turning points. To graph a polynomial function, you need to make a table of values to find several points and then connect them to make a smooth, continuous curve. Knowing the end behavior of the graph will assist you in completing the graph. So let's look at this one. We have to the third power, okay? So we have an odd function. We've got our table of values. We plot our points. And we know that the ends are going to go in two different directions. It could cross the x-axis up to 3 times or 1. It's going to be an odd number of times. This one crosses 3. So this is an odd degree polynomial with a negative leading coefficient. Notice that we end up going toward negative infinity. And it has 3 real zeros. Okay, let's try your hand at this. So which one of these graphs fit this function? So pause for a moment, then come back and check your answer. Well, we know it's an odd function, so this one's out, right? This goes in the same direction, this goes in the same direction, so it's going to be one of these two. And the leading coefficient of 1, and it's a positive leading coefficient, so it ends up going up. This one ends up going down, so that's why C fits. Without having to do the table of values, we can see why that fits. Now I'm going to go back and let you look at example 1 for a little bit. Look at that table of values. One of the zeros occurred at 1, so when x was 1, we have a 0. Another 0 occurred between -1 and -2. Because f of x is positive when x is -1, so you have a positive answer, but then at -2 it changed to a negative answer. So whenever you see a change in signs like this, you know that you have a 0 somewhere between x -1 and x is -2. And all polynomial functions are continuous, so we know that there's a 0 somewhere between these two values. It's going to cross the x somewhere between there. So if the value of f of x changes signs when one value of x to the next, then there is a 0 between those two x values. Between the two x values. This idea is called the location principle. So here's an example of the location principle. So let's locate the zeros of a function. We're to determine the consecutive values of x between which each real zero of the function that's given is located, and then draw a graph. So we're going to make a table of values, and since the f of x, or since this function is to the 4th degree, it will have either 0, 2, or 4. I usually think of it as it can have 4, 2, or 0. If it was a 3rd degree, do you remember what that would be? It'd be, if it was to the 3rd degree only, it would have 3 or 1. It'd have an odd answer for the number of real zeros. So let's look for the changes in the signs. So there's a change in sign from here to here, from here to here, from here to here. And this helps us know, if we find 1, we know we've got at least 2, because we know we've got to have 4, 2, or 0. If we find 3, we know we need to keep looking for that 4th one, because if it's an even exponent, you know you have an even number of real zeros. So that helps you know how many answers you're looking for. So we're going to look at the values of f of x to locate the zeros, and then we're going to sketch a graph. So we plot the points that were in our table of values, and we sketch the graph of the function. There are zeros between x equals -2 and -1. Right here. There's a 0 between x is equal to -1 and 0. So there it is again. There's another 0 between 0 and 1. And there's another 0 between 2 and 3. Okay, time for you to check your progress. So to determine the consecutive values of x between which each real zero of the function is located. Now what I did is I entered this function in my graphing calculator, and I go to my table and I study the table of values to see where are the zeros. So you can pause for a moment, then come back and check your answer. Well, you know it's either going to have 3 or 1 real zeros. If you find 2, you need to look for the third. There is a real zero where x is equal to -1 and x is equal to 0. There's another between 0 and 1, and the third is between 3 and 4. So these are very close together, but you know if you've got 2 and this is at odd power, you got to find the third one. So don't stop looking too soon. Okay, this graph shows the general shape of a third-degree polynomial. Point A on the graph is a relative maximum. Notice that it's higher than the points around it. Except for the ends, this is the highest point, and the relative minimum is that lowest point. Now the maximum minima, if you're referring to both of them, they're known as the extrema. And these are also known as turning points. See, this is where the graph turns and changes the other direction. So point A on the graph is a relative maximum of the function since no other nearby points have a greater coordinate or a greater y coordinate. The graph is increasing as it approaches A, and it decreases as it moves away from A. Now let's look at point B, known as a relative minimum. Since no other nearby points have a lower y coordinate, the graph is decreasing as it approaches and it increases as it moves away. So these maximum minimum, as I said, are the extrema. You know, some odd functions like x to the third, they have no turning points. So not all of them have turning points. A polynomial with a degree greater than 3 may have more than one relative maximum or relative minimum. Okay, so let's look at this function. We're to estimate the x-coordinates at which the relative maxima and relative minima occur. So let's look at the table of values. There's a 0 here, somewhere between a -2 and -1. And then it's increasing, and then whoop, it starts to decrease. So that must be our maximum. So it decreases, then whoop, there it starts to increase again. So that indicates a relative minimum. So you're going to see where it goes the highest before it starts going back down, and goes the lowest before it starts going back up. That's how you can look at a table of values and find the extrema. And here, the value of f of x at x equals 0 is greater than the surrounding points. So that's a maxima, a relative maximum. And the value of f of x at x is equal to 2 is less than the surrounding points, so there must be a relative minimum near x equal 2. And you can use the graphing calculator to find the relative maximum and minimum. You go to that calc menu, and then you either click on maximum or minimum. You're going to select your left bound, and then again your right bound. And remember, you're reading your graph left to right. So it may be above or below the graph, but it has to be left of your point, reading left to right. You press enter twice, and then it will give you your answer after you've done your right bound. The estimates for a relative maximum near x equals 0 and a relative minimum near x equals 2 are accurate. Okay, time for you to check your progress. So pause for a moment, then come back and check your answer. Well, when I entered this into my graphing calculator, I found that yes, there was a relative minimum at 0. The actual point is 0.2. And then the relative maximum is at a -2, 6. but they're just asking the relative minimum maximum. It occurs where the x coordinates are. Okay, the graph of a polynomial function can reveal trends in real-world data and is often helpful to note when the graph is increasing or decreasing. So let's use this in a real-world situation. The weight in pounds of a patient during a 7-week illness is modeled by this function, where n is the number of weeks since the patient became ill. So first of all, we need to make a table of values, and we're going to graph each of these points. Okay. So let's describe the turning points of the graph and its end behavior. Well, there's a relative minimum at week 4. So the function, it's approaching positive infinity as n approaches positive infinity. Now, what trends in the patient's weight does the graph suggest? So the patient lost weight for each of 4 weeks and after becoming ill. Then after 4 weeks, the patient gained weight and continues to gain weight. Is it reasonable to assume the trend will continue indefinitely? Well, I'd certainly hope not. The trend may continue for a few weeks, but it's unlikely that the patient's weight will rise indefinitely. So now, time for you to check your progress and answer a few questions. If I was you, I'd get out my graphing calculator and I'd enter the function in and I'd compare, but be very careful. There's a few things you need to watch for. So come back and then check your answer. Okay, plotting the points. When I was looking at my table of values, I saw a relative maximum on my table of values at 2. This looks awful similar to this, but notice this is not a maximum at 2. This one has a maximum at 2, so that's why I chose A. Now we're to describe the turning points of the graph and its end behavior. So look it all over in your selections and then come back and check your answer. Well, we sort of discussed this in the previous one. The relative maximum is at month 2, and it decreases as the months increases. So what trends in the amount of rainfall received by the town does the graph suggest? So the rainfall looks like it increased the first 2 months and then it decreased. Is it reasonable to assume the trend will continue indefinitely? No. Now, if you could start predicting the weather that closely so that you can say this trend continues indefinitely, you can make the big bucks. All right, you're ready to begin the exercises. Good job.